So I've plotted over here the two functions. So the first function is the function in cyan, or the blue color for people like me, is the velocity potential that is given by a times x square minus y square. So that's a family of hyperbolae with the asymptotes as x equal to y and x equal to minus y. The white color curves are the curves of iso psi, that is iso stream function. So the stream function is given by twice axy, which is a set of rectangular hyperbolae. So the asymptotes in that case are the x-axis and the y-axis. And as you can see, the iso lines of phi and psi are in fact orthogonal to each other, and this should not at all come as a surprise because that's how we had proven it in the previous section. So proceeding further, we can easily show that psi equal to 2axy and phi is equal to a times x square minus y square. They are a set of orthogonal functions, that is, the iso psi and the iso phi lines are orthogonal, that is grad psi dot grad phi is equal to 0. So this much is clear by now. But if this is a solution, then psi is equal to a times x square minus y square and phi is equal to 2axy is also a solution. So now if we focus on these particular solutions, so psi equal to 2axy, if I draw the x-axis and the y-axis, the white curves, the iso psi lines, that is this particular function, is actually a flow like this, and it is a form of an idealized flow around a right angle corner. So there is no flow which crosses this line. Similarly, there is no flow which crosses this line. So the flow sort of, so this is the streamline also. We have also shown this in the previous section that this is also the streamline. So the flow happens like this. So this is the flow in a corner. I have not plotted a lot of contours, but I'll be sharing the code with you, in which case you can easily increase the number of contours and you will see that there will be lines like this as well. And of course, lines across which there is no flow, that are behaving like solid boundaries, they are also a streamline. So this is actually one streamline. This is also one of the streamline. So it is easier to visualize flows with the help of isostream functions, and isostream functions are also streamlines, but it is not so easy to visualize flows with the help of velocity potential. But the velocity potential, of course, has its own merit. It can be used to discern other things. But for ease of observation or the convenience of reading out a given figure, it is often beneficial to plot everything in terms of a streamline. So now let us proceed further. Let us consider the, the flows because of the point sources. So psi is equal to minus gamma by 2 pi ln square root of x square plus y square. So this was the solution for the stream function due to a point vortex at the origin. Point irrotational vortex at the origin. So let us see what the corresponding velocity potential will be. So if this is the stream function, the velocity u will be del psi del y. So let us differentiate this. So it will be minus gamma upon 2 pi. So log of this, so derivative will be this. Then the derivative of this, basically it's just chain rule times 2y. So this 2 cancels out. So it's minus gamma upon 2 pi y upon x square plus y square. Similarly, v will be equal to minus del psi del x, and we just follow the same chain of differentiation and we will obtain minus gamma upon, rather this minus will vanish because of this negative sign. So it will be gamma upon 2 pi x upon x square plus y square. So we can make use of the definition of the velocity potential. So this will be equal to del phi del x and this will be equal to del phi del y. So we can integrate this. So we will obtain phi is equal to minus gamma upon 2 pi times y. So this will be tan inverse. So when you integrate this with respect to x, so this will be plus tan inverse x upon y upon y. So this becomes minus gamma by 2 pi tan inverse x upon y. Similarly, I mean, there will be a constant also. So in fact, let me do it properly. So del phi del x is equal to minus gamma upon 2 pi y upon x square plus y square, and when you integrate this with respect to x, this will be minus gamma upon 2 pi y tan inverse x upon y, y cancels out, plus function of x, other function of y. So this will be minus gamma upon 2 pi tan inverse x upon y plus fy. So del phi upon del y would be minus gamma upon 2 pi 1 upon 1 plus x square upon y square times minus x upon y square is simple chain rule for this, plus df dx. So this comes out to be, so this minus minus becomes plus, so gamma upon 2 pi y square upon x square plus y square times x upon y square. So this y square cancels out. So in fact, this will be simply x upon this plus df dx. But from this expression, we have uh, v, which is essentially del phi del y. So del phi del y is gamma upon 2 pi x upon x square plus y square. So when we equate this expression and this expression, we will obtain gamma upon 2 pi x upon x square plus y square is equal to gamma upon 2 pi x upon x square plus y square plus df dx. So these two terms cancel out. So that implies df dx equal to 0. That implies f is constant. So utilizing these two, we obtain an expression for the velocity potential corresponding to this, and so the velocity potential is equal to gamma upon 2 pi, rather minus gamma upon 2 pi tan inverse x upon y.